Good morning, everyone. This is Michael Dong, and here is video number 14 on HPLC pumps, operating principle, types, and trends. Let's start with the agenda. Section 1 is overview of the principle and types. We'll talk about requirement, operating principle, and different types of pump. Second, we use a case study of an HPLC pump. We use Agilent 1290 binary UHPLC pump as an example. And then we talk about some modern pump trends. We start with a glossary of the key terms and with some of the explanatory notes. A piston is typically a rod made from sapphire, ceramic, steel, or alloy. A piston typically is reciprocating, driven by a motor within a piston chamber in the pump head. To drive the piston is a mechanical unit called the drive, which actuates the pump's back and forth directions, typically powered by a motor. In the modern pump is a digital motor. If you have an analog pump, you need a circular cam, and a lot of them are driven by a screw drive mechanism. A pump has a metal body, typically stainless steel 316, with one or more multiple chambers to accommodate the piston and check valve, etc. A check valve is a device which allows liquid to flow in one direction, typically using a bore and seat combination arrangement that works with gravity to close and to open. A proportionating valve is a white Teflon block with typically 4 solenoid valves. Each are connected to a separate solvent line to allow blending of a mixed mobile phase using a single pump. Proportionating valves are very common in quaternary or quad pumps. Mixers are generally needed, are required to ensure adequate mixing of the blended mobile phases. Here in this table, we mentioned about the requirement for the analytical HPLC pump in terms of pressure rating, flow range, inlet flow path, solvent blending capability, integrated information, and system control, right? So here are some of the requirements, some of which has been explained a little bit before in previous videos. We talked about HPLC versus UHPLC, different pressure limits requirement in terms of PSI and in terms of bars, and intermediate system, also microsystem with lower flow rate. So the requirement for pumps are flow path consisting of metal and other material which is compatible to some common HPLC solvent. A pump have to allow for accurate blending for 2 or more solvent and also need to be accurately have accurate compositional control for either isocratic for blending or gradient operations. So all these solvent need to be degassed. Also, you need very precise operation with long-term reliability, particularly in the pump seal. Pumps are controlled by a controller, ultimately by a CDS or chromatography data system. The white paper that some of these data were coming from was primarily from this person here, Mrs. Soyak from Agilent, and the paper was published in 2019 as a white paper. Here's a schematic of the reciprocating piston pump, which is very common. This is a very simple single piston reciprocating and allow us to demonstrate the operating principle where we have a pump head and we have a sapphire piston about 100 microliter with a piston seal driven by analog motor with a circular cam which is off center so that when it's turning the piston's being driven back and forth, and there's a spring over here which allow piston to return, and you have 2 check valves. These are both driven by gravity. You have a ruby bore on a sapphire seat. We need these semi-precious materials because they are very hard. So when the piston is going back, the inlet ball flows up, allow solvent to come in, and when the piston is driving into the chamber, uh, the inlet valve closes and the outlet valve open. So the problem with these pumps is pulsating. So once again, here a summary. A motor-driven cam drives the reciprocating piston to deliver solvent through a set of inlet and outlet check valve. Drivetrain can use digital motor. In most modern pumps, it's driven by a digital motor. And also, most use direct screw drives to transfer the circular motion to linear motion. A pump has typically a stainless steel 316 block containing drilled chambers to accommodate the piston seal, and check valves. Now, most modern pumps are in this category called dual piston in series. There's also dual piston in parallel, which is less common. Let's focus on dual piston in series. Piston driven independently by two separate digital motor and two pistons. These pistons can be equal size, or the first piston can be slightly larger. So this offers higher compositional accuracy. Some example was Waters Alliance 2690, Acuity UPLC H class, or the Agilent series, and Shimatsu Nexera and 10A system. I think the only one that's doing dual piston in parallel is the Vanquish from Thermo Fisher Scientific. There's also two important categories on how the solvent are mixed. Okay, the two type are high pressure mixing, typically delivering higher performance, and these are usually binary pumps, or low pressure mixing, typically quad pump or quaternary pump, equipped with a single pump with a proportionating valve, right? So we talked a little bit about the high pressure mixing pump. These are binary pump with two separate motors. They have something called lower dwell volume, okay, which make it very compatible with LC-MS spec on low flow application. It actually delivers higher compositional accuracy. However, they are more expensive. And here are some examples. A low pressure mixing pump are actually less expensive, even though they support mixing up to 4 solvents. So they are used in multi-solvent pumps, mostly quaternary pump. They are less expensive because they only have one pumping mechanism and can draw solvent from a proportionating valve connected to 4 solvents. So they are very helpful to do method development. Example shown here from Waters Alliances to Acuity to Agilent quad pumps. Here is a case study. We're using the 1290 Infinity 2 binary pump as an example, which support floats up to 19,000 psi or 1,300 bars. We show the front view and some internal component here. Diagrams courtesy of Agilent technology. So shown here is 2 channel, the 2 separate pump. These are dual piston in series. So you have a primary pump head, secondary pump head. There are also accessory. There's an automated switching valve, which allow you to do primings in the automatic fashion. And there's also a degasser built in, and a pressure sensor. In the next slide, we show you an actual schematic, which probably is clearer, showing you the 2 pump heads, channel A and channel B. Now, even though it only supports binary mixing, you can actually connect 4 solvent to it, being controlled by a low pressure switching valve here. So you can either select A1 or A2 or B1 and B2. And a built-in 4-channel degasser. Here is an automated switching valve, kind of automated purging valve, and also a mixer called a jet weaver mixer. Yeah. We talked a little bit about the technical pump detail. Built-in vacuum degasser is a dual piston series with separate drive mechanism for each piston with a digital motor. The piston actually made with ceramic with a volume of 100 microliter. However, it does support automated variable stroke volume, so each stroke can be 5 microliter to 100 microliter dependent on the flow rate. The inline filter built-in, inline pressure transducer, and jet weaver. Jet weaver have two sides. These are the high-tech mixer, and most of the QC lab would select that 100 microliter larger mixer. And for high throughput screening, you probably want to select the 35 microliter mixer. But the 100 microliter mixer gives you more thorough blending. Some of the modern pump trends are shown here. The big takeaway is that most pumps are dual piston in series, so they are more sophisticated pumps, also higher cost. They also have low dwell volume, particularly for UHPLC application. So high pressure mixing pump are really for micro LC and the high throughput screening applications. They are higher performance, however, they're also more expensive. Low pressure mixed pump are much more common, great for method development for routine assay. Pumps have much better precision and reliability compared to pumps of the previous decades. Most are dual piston series, some are in parallel. Most of them have variable piston stroke. Some support micro piston applications, such as Shimazu pumps. They do use a 10 microliter micro piston. And most of them would have piston seal wash. So modern pumps have low dwell volume or gradient delay volume, definitely less than 1 mil. Most of them, binary pump is less than half a mil. And for UHPLC, typically dwell volume are in this range of 0.1 to 0.4. For UHPLC, the common interpretation of the pressure rating is over 15,000 psi. Once again, two references quoted here. First one is analytical chemistry, and the second one is the white paper that can be downloaded for free from LCGC magazines. Here's my summary and conclusions. And we talked about requirement, operating principle, different types, and case study with Agilent 1290 binary pump, show you some internal component and schematic, and also some modern pump trends. On that note, thank you for your attentions, and we finish video number 14, HPLC pump operating principle, types, and trends. Please, once again, subscribe for future video where we talk about auto sampler in more details, UV detectors, and also CDS. Okay, see you next time.